welcome to our studio guests today and to fellow travelers out in cyberspace, thanks to that non-stop stream of zeros and ones, the zero that we are looking for. My name is Peter Gobetz, co-founder of the Zero Project and moderator of the International Conference/Workshop on Zero. The Zero Project is a three-stage affair. There's a book project, there's this associated online event, and then there's the in-depth research program. But today, session number 4. We welcome two of the other contributors to the monograph on Zero book project, Dr. Marina Ville at the University of Paris and Dr. Avinash Sathaye in USA. Both speakers will address the highly controversial issue of division by zero, and as such, stress the unrivaled significance of zero in mathematics. We also welcome back our two speakers from last week's session, who will serve as panelists today, Dr. John Marmish in California and Dr. Anders Erik Hoogkarspel here in Holland. Marina, if I may now invite you to introduce yourself and give us a brief presentation of your paper, please.
Hello. Well, first, it's very nice to be here. I hope at some point we all meet in person. So I'm going to talk about dividing by zero, why it's at the same time not really possible, but on the other hand, it's something we really need to do, and how we can indicate a couple of ways to address this question. So dividing by zero, it's one of the prohibitions which even non-mathematicians know, even from elementary school, they remember it. And so let me just recall why, because it's so ingrained that it feels sometimes like driving through a red light, something you just don't do, but there's a reason. So please can I have the first slide? So so this is a regular division, like I divide 100 by 4, I get 25. And then what happens is that if I multiply 4 by my result, 25 times 4, I get back on my feet, I get back to 100. So division, multiplication are inverse of one another. Now suppose instead of dividing by 4, I divided by 0. So I say 100 divided by 0, and since I don't know what it is, I wrote it as a little question mark. So if I could do that, then I would do the same thing. I would then divide 100 by 0, get question mark, and then multiply question mark by 0 and get 100 again. But of course, this doesn't work because we know that any number multiplied by 0 is equal to 0. So that's why dividing by 0 is not possible. So if it was possible, what would the result be? So let's do some experiments. Instead of dividing by 0, we divide by smaller and smaller numbers. So can I please have slide number 2? So so you see I divide by smaller and smaller numbers, by 0.1, 0.01, etc. And every time I get a bigger and bigger number. So in a sense, what I want to say is that if I divide 0 is smaller than all the other numbers, for the rigorous listeners, I will not be mentioning negative numbers here. All numbers will be positive. So 0 is smaller than all the other numbers. Then if I take 1 over 0, I need to have a number which is bigger than all the other numbers. And so that number is infinity. So I can write 1 over 0 is equal to infinity. And infinity being, I haven't defined it. I just say it's the one candidate to be the inverse of 0. So we're going to see a bit how we can make sense of this. And one way of making sense of it, but which I will not elaborate on, but is connected to geometry. I just want to add as a parenthesis that in geometry we also have we also like to introduce infinity. So can I have the third slide, please? So you see, it's also something we learn as children, that two parallel lines never meet, and two non-parallel lines meet only once. That's one of Euclid's axioms. And so when we look at the train tracks, so you have a bunch of parallel train tracks, and of course they don't meet. If they met, then the trains would crash. But when you look at this picture, you still want them to meet, quote unquote, at infinity. And so there's a branch of geometry called projective geometry, where you add a point or points at infinity. And it can be a very useful procedure where you can get results even who are important for non-projective geometry. So that's one direction to go to define infinity, but I'm not going to take it. I'm going to just consider it involves introducing complex numbers, and I don't want to go into that. So I'm going to stick with the real usual numbers. And suppose I have added this extra number, which is called infinity. So now that I have an extra number, I want to use it, to compute with it, as we do with numbers. So some computations make sense. If I take infinity plus 4, well, clearly I will have, the result will be infinity. Infinity times 4, the result will also be infinity. 4 divided by infinity, the result would be 0. And this is intuitive. If I take 4 centimeters and I divide them into infinitely many parts, then clearly each part of equal length, clearly each part will have length 0. So this is, so some computations make sense. But now what happens if I want to say 0 times infinity, 0 divided by 0, infinity divided by infinity? And there I run into problems. So let's please see slide number 4. So in this slide, you see I divided 2 again, since infinity is not something I can really put my hands on. I experimented and I divided very small numbers by other very small numbers. So you see in the first line, I have 2 on top and on the bottom. I have 2 very small numbers which are equal to one another. And so clearly when I divide them, I get 1. But the second line, I get a very large number, and the third line, I get a very small number. So actually what matters is not just the fact that the numbers are very small, but how small one number is in relationship to the other. If I divide this very small number by a number which is much smaller than the very small number, I will get a large number, and vice versa. If I divide a very small number by a number which is very small but not as small, I will get a large number. So what matters is how small are the very small numbers in relationship to one another. And so maybe now I will, at this point, maybe some listeners can think that this is sort of hair splitting. I mean, dividing 0 by 0, it sounds more like science fiction than something useful. And so I will try and convince you that it does not. And can I please see the fifth and last slide? So you see here, I have a curve, the top black curve, and I want to measure its length. So we know, and I assume I just have a ruler. So with a ruler, I can measure straight lines, but I can't measure a weird shape like this. So clearly what I want to do is to approximate the curve by straight lines. So I have a first approximation, which is not very good, which is by red lines. And then a second approximation, which is better, by the blue lines. So the blue lines, I don't know if you can see it on the pictures, the blue segments are smaller than the red segments. And ideally, if I want to have a perfect measure, I need to approximate to have segments by segments which are really small, ideally infinitely small. But then if my segments are infinitely small, I will have infinitely many of them. And so I will find myself in a situation of infinity times 0. So that's one case where there's a really concrete reason to understand infinity times 0. And now for 0 over 0, let me give another example. After these 2 years of pandemic, we've all become used with, we all hear numbers every day, and we've become used to interpreting numbers. And so, for example, one thing which we now all understand is that if I say today, this week, there are 10,000 new COVID cases, and last week there were 15,000 new COVID cases, it is actually, it's 10,000 new cases is a lot, but it's actually a much better situation than if I say today there are 1,000 new COVID cases, and last week there were 200 new COVID cases. So what counts here is not the number of cases, but the trend, the rate of change. And so rates of changes, which is called in math derivatives, it's something very important at the basis of, for example, Newtonian mechanics. They give us an equation for the acceleration. A force gives you the acceleration. So how the speed changes, the rate of change of speed, which in turn gives you the rate of change of position. So it's important to understand these rates of changes. And speaking of speed, when I'm on a road, my position changes continuously. So ideally, I want the information of speed, which also changes continuously. And so how do if I compute the speed over 4 hours, then I divide how much I've driven, the distance divided by the time. But I want to do the same if my position changes continuously. So I'm going to end up taking an infinitely small instant, and how much I have traveled during this infinitely small instant, which will be an infinitely small distance. And so I'm going to divide infinitely small distance by infinitely small time. So 0 over 0. So these two, what I've shown you with the curves and the rates of changes, the derivative, these are integration and derivation, the two operations at the basis of calculus. And I hope by now I've convinced you that the important tool was infinitesimals, that is infinitesimally small quantities, which are not quite 0, but which are infinitely small and which have different order of magnitude with respect to one another. And these infinitesimals were what the forefathers of calculus dealt with. And for a couple of centuries, it was extremely successful. And they computed with infinitesimals, and they got zillions of results, and there was really an explosion of new science. And in the 19th century, mathematicians started taking a step back and looking at infinitesimals and trying to make more rigorous sense of it, because you notice I haven't defined anything. I've been doing what mathematicians called waving my hands. So then by Cauchy in France and in Weierstrass in Germany, they gave a rigorous foundation for calculus, and infinitesimals were swept under the rug. Their definition doesn't use infinitesimals. It uses something called limits, which I will not describe. And infinitesimals remained only in people's scrap papers because they're so useful to compute. But they did not, they left the forefront. And in the 20th century, and so calculus and what's actually the more advanced form, which is analysis and differential equations, partial differential equations, all that continued progressing. And then in the second half of the 20th century, someone called Abraham Robinson reintroduced infinitesimals and gave them finally a rigorous founding, which is something which Weierstrass could not have done in his time, because Robinson used 20th century logic. So, but then it was a bit too late. He created what's called non-standard analysis, but it remained non-standard because Weierstrass and Cauchy's definitions were still completely ruled the world. So who knows what would have happened if the infinitesimals had been justified, let's say, earlier. So thank you very much.
Very much, very interesting, especially for people who are not accustomed to this depth of knowledge about mathematics. Avinash, would you take the floor, please?
Okay. Right. So I will. I need my slides displayed. Oops.
Oh, sorry. Briefly, we've sort of skipped over that.
Oh, yeah. Well, this is just the introduction here. Is there any way of making this full screen for me? Oh, yeah. I see. Okay. So I will. So when and how to divide by 0 is my title, and let's go to the next. Okay. So this is what Marina just talked about. Thou shalt not divide by 0 is one of the well-known 10 commandments of mathematics. There are posters displaying all 10 of them. So next, in routine mathematics of real numbers, it is well known that setting 1 over 0 equal to c for some real number c leads to serious mathematical inconsistencies. So letting, I guess Marina kind of explained this already. Letting 1 over 0 equal to c leads to 1 equal to 0 times c, which means 1 is 0, and that makes further calculations meaningless. So we will try to explain how defining 1 over 0 equal to infinity. Well, don't ask what infinity is. It's a new symbol we created, a new number we created. And making proper laws to handle this newly created number infinity leads to useful, correct calculations. With proper care, it leads to the idea of limits in calculus. It also leads to other algebraic operations in newly corrected systems. I'm not going to address it too much right now, but so you have already seen Marina's presentation. She gave a detailed discussion of the earlier mathematical developments. Several mathematicians have also made attempts to develop an expanded number system, and which will let us get around the difficulty by introducing a plethora of zero-like entities which avoid the logical flaws. One of the prominent works is by James Anderson. Actually, I didn't. I should have mentioned the real numbers. But anyway, there are several, okay, here it is. There are several attempts along the same lines using trans-real numbers with various degrees of complication. My aim today is to describe a system originating from Indian algebra, which has been defined since Brahmagupta, which means the system is defined, and further enhanced by Bhaskaracharya. So I will attempt to present the main structure of these developments without getting into complicated arguments. These details will appear in my article in the Zero monograph. We shall begin with the definitions in the books by Bhaskaracharya, even though these definitions go back to Brahmagupta in 7th century, or perhaps earlier. The first book of Bhaskaracharya used here is called Bija Ganita, and I will shorten it as just Bija. And by so these are the rules laid down. By multiplication with 0, the answer is 0, whereas Khara results when a number, or called Rashi, is divided by 0. So that's a new number. So first comment is, usually Rashi refers to a positive integer, or at least a positive real number, although it may also be negative when declared as such. However, 0 is not among the possible values at this stage of discussion. So 0 over 0 is not formally defined here. It will be defined a little later. So the second comment is, here Khara, or 0 divided, is a technical term, meaning something which with denominator 0, it is simply a new number denoted by x over 0 and does not produce any ordinary numerical values right away. That's the whole point of this discussion. In the second book called Lilavati, we find additional information in Lilavati 46 and 47. So 0 plus or minus 0 is 0. Powers of 0 are 0. This is all usual. A number divided by 0 is Khara, and which means 0 divided. Kha stands for 0, and Hara is the division, so divided by 0. And 1 multiplied by 0, usually you don't give it a name, but it's called Kha Guna. So multiplied by 0. It evaluates to 0. However, one should consider it as a 0 multiplied number during the rest of the operations till the final answer. So one comment is, for a not equal to 0, we may deduce that a times 0 over 0 is equal to a, because or it is a times 0 over 0. So you can either happily cancel the zeros here, or say that it is a times 0 over 0. So this quantity 0 over 0 must be an idempotent. That's a term from modern algebra. But all it means is an element in your system such that when you square it, you get back the same answer. So something which solves x squared equal to x. Now, the usual such idempotents that we know about are, here I am saying, so we expect this to be 1, but 0 also has the same property. 0 times 0 is 0, and 1 times 1 is 1. So the numbers which are Khara and Khaguna and the usual numbers are in 3 separate compartments. I'm going to set up the system now, and at a time we combine only numbers of the same type. Now that's not a normal algebraic operation, but to get to this setup, this is a conclusion from our actions. So in this view, it says a over 0 plus b is simply disallowed, because a over 0 is a Khara number and b is a real number. So only multiplications or division by 0 allows one to go from one compartment to the other. So for convenience, let us make these definitions using modern terminology. it is clear that if we want to multiply or divide by 0, then we need a placeholder formal symbol for it. So that it does not get evaluated to 0 until the formal rules have been properly applied. So as usual, I say R is the set of usual real numbers. I will use epsilon to stand for the multiplier 0. We shall also use the infinity symbol, infinity, to represent the reciprocal of 0. So for 1 over 0, the symbol should await for full simplification before evaluation. So that's the main point. For any non-zero a in R, we write a epsilon to denote multiply a multiplied by epsilon. It will be eventually 0 unless some other operation intervenes. This a epsilon is said to be a K-guna. Similarly, we also define a K-hara as any number with 0 in the denominator, and thus for any non-zero a, we define a infinity to be the a K-hara. So formally a times 1 over 0, also written as a infinity. So now I have built up 3 sets of real numbers really. These are copies of real numbers. So the first one is just the real numbers, the usual. Second one is the set of K-gunads. So it's epsilon times R. And the third one is the set of K-harads, which are the numbers divided by 0. So our formal number system shall be generated by these sets. The word generated is in double quotes because that needs some work to create the generation in a logical way. So in the monograph paper, we explain in detail what the generation is, and we set up a simplifying operation to get the resulting evaluation. So you shall not make a number out of it until you have done the simplification. I will only give the conclusions from this simplification. So by our rules, the final number will turn out to be of the form a infinity plus b plus c epsilon. It's a K-hara, real, and the K-guna. But out of these 3 terms, only one survives, and that I call a winning rule, but it's not by declaration that only one survives. We will have to say, well, what happens if I multiply 2 of these and then what will survive? So I can take a square and I would get things like a squared, infinity squared, and so on. So this is something we discuss little later. Okay. So let us go to the next. Okay. So these are the so-called winning rules. To clarify the simplification described above, we have described winning rules in the paper as follows. Infinity wins over the rest. So it says if a is not 0, then a infinity plus b plus c epsilon is simply a infinity. Reals win over the K-guna. So if b is not 0, then b plus c epsilon is just b. The c epsilon doesn't count. And if the K-guna, unfortunately, loses to all others. So if a and b are 0, then a infinity plus b plus c epsilon simply reduces to c epsilon. If c is also 0, then we get the 0 in the real numbers. If c is not 0, then it stays as a K-guna. Okay, so now let me explain why I got into this in the first place. So while reading through the work of Bhaskaracharya, I found 3 specific exercises posed by him which involve the operation of division by 0. The first of these is an exercise which can be explained as the idea of limit in modern calculus, something Marina discussed in detail. So indeed, Bhaskaracharya himself commented, there's this core, I see the typo here, I forget the extra letters. Kahara is of great importance in astronomy. We find that it was used to derive, again a typo, the notion of instantaneous velocity. Usually for movements of planets over long periods, again a typo, this whole thing is full of typos. Planets over long periods can be handled by average velocity suitably modified. So I'm going to explain what that means. However, for analyzing the problem of calculating eclipses in detail, so that's when the sun or the moon get covered by Earth, the sun gets covered by by Earth, and sun gets covered by moon. So we need to use instantaneous velocity for predicting the movement over small periods of time, often only a few seconds, even fractional seconds. So Bhaskaracharya had developed the concept and used it for his calculations in astronomy. So he had specifically calculated the movement along the tangent line. He didn't call it a tangent line, but the description is clear. The second and the third exercises, however, give answers which cannot be explained by calculus idea of limits. In fact, most commentators have declared them as defective, and this has been described as a serious error by Bhaskaracharya, whose work is perfect otherwise. So I was trying to understand what caused this so-called mistake. Where did it come from? So my threefold number system resolves the problem of explaining the mistake. I will next analyze each exercise in detail and explain how it fits the threefold number system introduced above. I often wondered why Bhaskaracharya did not pursue ideas about this number system further. I suspect that he did not find any practical use for them in his treatises. His treatises were mostly on astronomy, and the first exercise was enough for that. So maybe he left them as isolated ideas. I also wonder if by pursuing them, he could have discovered more modern mathematical ideas, but these are just musings. So the first exercise is from Leelavati, number 48. And this, by the way, is a typo also, but it will be clear. So in words, it says, what number, say t, is such that if we multiply by 0, the number obtained when you add t half, t over 2 to t, what is missing here is, and then multiplied by 3. So that 3 is missing here. You will see it in the next item. And when is the result equal to 63? That's the exercise. So in algebraic terms, this means this 3 times t plus t over 2 multiplied by epsilon and divided by epsilon. When is it 63? Well, by our rules, this will simplify to the simple equation. 3 times t plus t over 2 is 63, and you get a nice answer. Okay. So this emulates what Bhaskaracharya was doing with instantaneous velocity. The epsilon here does stand for a small number. Now the second exercise is from Bijaganita. And this Bijaganita says, well, I will give you just the modern format. But is a Rashi or a number t such that there is a complicated expression here. So t infinity, so t times infinity, plus minus some large number, any number actually, whole quantity squared plus the same number and multiplied by epsilon, this first two entries. When does it become equal to 90? So this is supposed to reduce to t squared plus t equal to 90, and then you go ahead and solve by the usual methods. But this reduction to the simple equation needs the simplification rules that I have introduced. So let me go at them step by step. So first, by the winning rule, this t infinity plus or minus this large number, it simply reduces to t infinity. This is the winning rule for the infinity. And that's why he is happily putting plus or minus. He doesn't care what it is. Then unless, so if you just reduce it to t infinity, then the first quantity becomes t squared infinity squared. Unless we use the rule that infinity times infinity equal to infinity, equation becomes epsilon times t infinity times t squared infinity squared equal to 90. Well, if you look at the left-hand side here, the left-hand side, if you cancel the epsilon, it looks like t plus t squared times infinity. And that's supposed to be equal to 90. Well, this will not produce any answer because by winning rules, the left-hand side is a Kohara, whereas the right-hand side is an ordinary real number. They are in two different compartments. They can't be equal. So we note, and we actually deduce these rules in the paper, that if we use the property that infinity squared is infinity, then our last equation becomes epsilon times t infinity plus t squared infinity equal to 90. And now, so the infinity squared is gone, t squared is there. And so this reduces to t plus t squared equal to 90. And you have solutions. As usual, we discard the t equal to minus 10 because by convention, t must be positive. So this word Rashi that Bhaskaracharya uses is a flag to say it's not zero. Okay, so now the next one is even more complicated in some ways. So again, I will describe it in modern terminology. Start with an unknown number t, add in its half. So that is t plus t over 2 or 3t over 2. Then multiply by 0. So that's, you don't put a 0 there. You put 3t over 2 times epsilon. Then you square and add its root twice. So you square this number, 3t over 2 plus epsilon, then that becomes this, and plus its square root added twice. In this case, since we took a square already, its square root is already known to us, 3t over 2 times epsilon. You multiply it by 2. And now we thus have this equation. Oh, well, we don't have an equation yet, but the left-hand side is 3t squared over 2 times epsilon squared plus 2 times 3t over 2 plus epsilon. Now, just like infinity, epsilon also has the property that it's an idempotent. Its square is equal to itself. And we get 3t over 2 plus, is there a typo here? 3, yeah, there is a typo here. The square got lost, but when you correct the typo, it's 9t squared over 4 plus 3t. And again, this epsilon doesn't belong here. Oh, sorry, this is still the left-hand side. So he times epsilon. And then you finally are supposed to divide by 0. Then you get epsilon over epsilon, which is 1. And we get this nice equation, 3t, 9t squared over 4 plus 3t plus 15. Now you simplify this, and it's ordinary quadratic, so that's nothing new. It produces two answers, 2 and minus 10 over 3. And in the usual style, we drop the minus 10 over 3, since t is supposed to be positive. Okay. So what comes next? We have avoided several technical difficulties, actually, of generating all results, resulting numbers from the symbol infinity, along with its reciprocals epsilon. However, we note that the resulting full set turns out to be, I already wrote this, a infinity plus b plus c epsilon. And now, in our paper, this set is shown to have the structure of a ring, which we call the Bhaskara ring, in honor of Bhaskaracharya. Here, so it's b of x. This, what is it, this x here? Well, it stands for just a usual variable. So here, at this stage, b parenthesis x is just the ring of rational functions. But rational functions which are simplified and evaluated. So in modern terminology, this ring is full of really the field of, that's what I just said, is a field of rational functions, but equipped with operations which include the simplification. In the Bhaskara ring, there is no obstruction to dividing by 0. So let me make some final comments. One other topic from my paper is not present here. In it, I discuss several concepts in modern algebra which give generalizations of the ideas described here. So Marina did some of it already. One idea is an entity called an idempotent. So I have used this term several times. An entity stays unchanged when multiplied by itself. So 0 and 1 are clearly idempotents. So is the newly created infinity. And so another idea is to enable an entity x to be in the denominator by going modulo its annihilator. So this is something which happens in modern algebra. So this means, oh, sorry, go back a little. Okay, so this means that if you want to go, or if you want to put x in the denominator, but x is a bad number, there is some y such that x times y is 0, then you cannot divide by x. So this is what you do then is all these y's such that x times y is 0, you turn them into 0. So in algebra, it's called going modulo the set of such y's. When you turn them into 0, x is no longer a problem. I have given explicit examples of this in the paper, but I guess it's time to stop right now. So now, thank you very much for listening. And of course, all comments and questions are welcome. Thank you.
Thank you, Avinash. Thank you very much. We go now to questions back and forth between Marina and yourself. Marina, any questions for Avinash?
I just wanted to make sure I had understood properly. So the Bhaskara, he takes epsilon squared to be equal to epsilon and infinity squared to be equal to infinity. Okay, thank you.
Right. Those are the idempotents.
Avinash,
Yeah.
are we talking about Bhaskaracharya 1 or 2? 8th
Oh,
century?
this is 2, of course.
12th century, is it?
Yes, yes.
Okay.
One was the famous commentator on Aryabhatta.
Right. Okay, and you have any questions for Marina, Avinash?
Yeah,
We're running a little short on time because we've gone over
sure.
but it was so fascinating. It's good that it's on record.
Yeah.
Any questions for Marina, Avinash?
So I guess I was kind of disappointed that you dropped the projective, the completion of the complex numbers. I suppose you didn't want to introduce the complex numbers at this stage. So, I have read through your rest of the paper and I see the usual ideas well represented. So,
do you want me to take 1 minute to explain the complex number and the?
What I would prefer, Marina, what I would prefer is, the crux from our perspective, from the Zero Project. How do you connect zero and infinity in the Riemann space? Maybe you could just take 1 minute to explain that.
Well, you really need to go through the complex numbers because the usual numbers, they're on a straight line. But they, as you know, yet another rule is that you don't take negative numbers, don't have square roots. And so the Renaissance mathematicians introduced square root of negative numbers. And this was, and so there's a whole, so now there's a whole, the body of numbers became enlarged very much. And in the 19th century, they're called complex because for centuries people were uncomfortable with square root of -1. They computed with it, but they felt it was weird and not real. And also they were called imaginary complex. All kinds of derogatory names. And in the 19th century, all this was like late 18th, early 19th, the set of complex numbers was shown to be like a plane. The numbers were put in one-to-one correspondence with points in a plane, which I'm not going to spell out, but or I can spell out quickly. Like a plane has a grid, and so this line, the x-axis, are the real numbers. The y-axis are the multiples, the square roots of negative numbers, and all the points everywhere else are sums of both, like one real number plus one root of a negative number. So that's a plane. And so infinity turns out, infinity is where the direction where, like a bit in the picture with the train tracks, where a point goes when it becomes very big. But you see, since we're on a straight line, we can become big in two directions. Big, that means away from zero. And in a plane, we go away from zero in all possible directions. So you have to imagine all the possible. Actually, I had a picture I could have shown you, but no, I don't have it. I didn't send it. So imagine a plane, and at every direction they go all to the same point at infinity. And so eventually you end up with a sphere because they all the directions go towards the same point. So in essence, you take a plane and you add one point at infinity, and you sort of glue all the end points of all the lines together to that point at infinity.
So actually, the riddle of zero and infinity sort of become visible in the image of a sphere where zero and infinity are intimately interrelated, as it were, which
right,
is
they became poles of
of the sphere.
Right. Actually, if you'd like me, I can share. I can share a picture on my paper. I didn't send it because I didn't plan to discuss it, but I can share. I don't know if there's a possibility of
well, Marina, if you don't mind, I think you've explained it perfectly.
Okay,
We leave we leave something to the imagination of the viewers also, but the main thing is that they can always go to the monograph and delve into all of the depth that you've all put into it, and which I'm afraid, I'm sort of cutting short here impolitely, but we're already over an hour and we're trying to keep it maximum to an hour.
Okay.
So
I have one comment though. Can I say something, or maybe?
Yes, sir. Yeah, being so senior, how could I deny?
Well, I mean, I have a slightly different way of thinking about this and explaining. So, in complex numbers, there is a variable, just as there is an x in real numbers. In complex numbers, it's called z. And then the problem is z can be evaluated at all points of the plane. But 1 over z cannot be evaluated at all points of the plane. It fails at 0. So the main advantage here is, well, just throw it in. Put in 1 over 0 as an acceptable function. And that suddenly creates the complex sphere, the Riemann sphere, as it's called. And then you just do the ordinary algebra.
Well,
it's the rational functions of z.
Right. No, okay. It's the same basic principle that you had elucidated otherwise, that don't panic when you see a number divided by 0 or 1 over z, but approach it calmly and rationally, and it'll get you to where you want to go. Let's leave it at this for now. I really would like to bring in John and Eric. Do you have any questions for the speakers, even though you may be totally unacquainted? John?
I'm a non-mathematician, but I thought this was rather fascinating. It made me think of the discussion in Kant's Critique of Pure Reason about transcendental illusions. Kant had claimed that concepts like truth were sort of these parallel lines that, lead our thinking in a particular direction, but truth is not a thing so much as a direction. And it's a useful direction insofar as it organizes our thought. So are 0 and infinity something like Kant's transcendental illusions?
I don't know. I'm sorry.
I have the same problem. I don't know that concept right now.
I think this illustrates the interdisciplinary aspect that specialists tend to speak past each other. But it's the more important to make this point. John, please, I interrupted you. You were going to say?
Well, I was just going to say that I suppose my question boils down to the ontological status of 0 and infinity. So are they real things, or are they simply illusions? And maybe this also relates to Eric's paper.
No, I would say it's not. I mean, they are very much real. I mean, that's how the Brahmagupta created it. He just divided by 0. Not worry about it, and then try to set up an algebraic system just using that. I mean, so he was more of an algebraist than a geometer. So in algebra, you just make up symbols and give them meanings which are consistent, then you are through.
Eric?
Yes, thank you, both speakers. I was amazed that Dr. Marina did such a good job that even I could follow her paper and understand what she was trying to say. I was thinking about the demands for the right understanding of shunyata, which is that the emptiness must be empty of itself. So it's called shunyata shunyata. So I wonder if we could push the 0 that far. So could 0 be empty of itself? Could it be totally relative to all the other elements of the system? I was thinking, for instance, in the Riemann geometry, there is a difference related to 0 and infinity between a straight space, a convex space, and a concave space. But these three concepts of straight, convex, concave are maybe could be seen as relative to each other. So there's no absolute straightness, absolute convexness, or absolute concaveness. Could we go this far, that zero or a zero element in any mathematical system could be seen as relative,
Well, I mean,
determined by the other elements of the system?
yeah, I mean, you could say that actually the trans-real systems create lots of zeros. At each point of the real line, there is a whole neighborhood supplied, and that point is the zero of that at that place, but not everywhere else. So yeah, zero can be expanded into an infinity, and in some sense, the Kaguna does that. Zero times x. These are eventually they all become zero, but they are different in the system. And in fact, there was a quote from Ramanujan who sort of suggested that all numbers are in the infinity. He said he didn't create this object called R infinity, but he says they're all there. And when you divide them, they all go into zero. So he had a philosophical explanation of this, about the universe and the soul.
But I'm sorry, by Riemann, you mean that there are things which, you mean the curvature, things which are like this, or saddles, or flat?
Yeah.
Is that
Yes.
So
Yes, this is quite relative. I mean,
relative to what?
something is straight compared to concave or convex, and the other way around. So there's no absolute limit unless you introduce strict definitions, which make the whole system an absolute system with unchangeable limits.
Marina, yeah, is that clear?
Yeah, but straight is defined intrinsically. It's like the curvature is zero.
Yes, but for instance, the number pi is not absolute. It is only 3.14 in a flat surface. But if you introduce this in a convex space, then pi becomes smaller. It may be 2. If you use it in a concave space, it becomes bigger. It may be 4.
Okay.
That's an excellent point, Eric, because you're hinting at the larger context of where we want to go, whether zero, whether it was invented, whether it was evolved, and whether it's dependent on the context in which it appears. We want to go there eventually. This is actually a very good start. We've looked at it from both sides, and we'll definitely revisit it. So thank you all for your contributions. And what we like to do in all of these sessions, we like to end with a very quick survey, just a one-sentence answer to the following questions, and we'll take turns. We'll start with Marina. Was the numeral zero, was it discovered or invented? Marina?
Well, I'm
one sentence.
Oh, one sentence.
Discovered.
No, I'm intimidated by the presence of philosophers. So for mathematicians, actually, concretely, I know there's this general debate about mathematical objects, but as a working mathematician, I feel that mathematical objects are all real, all exist, all were always existed, and we discover them. Even the most abstract things, they're as real as the pots in my kitchen.
So you're saying
but it's more a practical. It's not a theoretical. It's just what I
Marina, discovered or invented? Discovered, I think.
Okay, discovered.
Is that what you said? Discovered?
Yes.
Okay. Avinash, discovered or invented?
No, I would say invented, because it's anyway. I mean,
right, clear.
It has many different interpretations these days, but
right. John and Eric have already ruled on this last week. So unless you've changed your mind, we'll skip to the next question. Was the transition, because this is all central to the Zero project, this is where we want to go, was the transition between the placeholder zero, which was there for a very long time, and the numeral zero, which appears relatively late in history, was that a gradual evolutionary process, or was it a disruptive moment in history? Marina?
I don't know, but it's a question I have. Yeah, I was wondering about that. Yeah, but I don't know. I'm not a historian.
So gradual evolutionary or disruptive disruptive moment?
I think it's gradual. I think, but I don't know. I really not.
No, that's fine. That's fine. We're just taking a survey. And finally, again, Marina and Avinash. Marina first. Is the concept of nothingness, is it or emptiness, if you prefer, is that trivial or profound, Marina?
Oh, I'm sure it's profound.
Profound. Avinash?
Well, yeah, I mean, it is profound, but in some sense, it's the obvious thing.
Okay. Thank you very much. I've maybe tried your patience a little bit here, but we're trying to focus this in a particular direction. So I'm now basically concluding this part of the session, but we're not done yet. So I'm just like to tell the viewing audience again and remind them that if you tune in the week after next, then we'll explore further related issues to pinpoint, if possible, the epicenter of zero. and in doing so, you'll be helping us to draft a roadmap for further research, because that's really the bottom line of all this, is we want to do further research to see whether we find fresh evidence of zero's invention, which today is still shrouded in mystery. Okay, but before signing off today totally, we have a very special treat for you in store. It's a very brief preview of a world premiere next week of the stunning exhibition organized by Professor Parthasarthya Mukhopadhyay in Calcutta, which Kevin will now screen.
Om Sthapakaya cha dharmasya sarvadharma swarupine avatara varisthaya Ramakrishnaya te namaha.
Zero. No single mathematical creation has ever been more potent for the general on-go of intelligence and power. In this engaging tour of pictorial history, the journey takes us through the Egyptian hieroglyphs, Inca quipu, Babylonian clay tablets, Mayan glyphs, followed by the great Greek civilization, the mighty Roman Empire in the West, whereas we also come across the Chinese rod numerals, the lofty philosophy embracing the concept of nothingness by the ancient Indian seers, which gradually paved the path for emancipation of zero as a number in its own right, till the Arabs in the East, and through them it went to Europe. Touching all these cornerstones, this bilingual panel exhibition tries to place the true genesis of our modern zero in its proper footing, an ode to nothing that is. Historical reconstruction of mathematical knowledge of ancient period is much like arranging pieces of an enormous jigsaw puzzle. Unfortunately, some of the pieces of which have gone missing. There are historians of mathematics all over the world who are trying to arrange the pieces, of course, according to their own stance, so as to make a pattern out of it. And the job is anything but easy. Often, the preconceived ideas come in the way of scholarly acumen. But of course, there are people who are trying to analyze the available piece of information and even lack of information with an obvious intention to try and make a pattern out of it. With every new piece being found occasionally, it destroys the existing pattern, and the journey continues. Where have the rest of evidences gone? Will our search ever find anything new? These questions you have inherited now, and the history of zero continues with you. History of zero continues with you.
So thank you all very much for watching. Until next week, Partha will be here in person to briefly introduce the exhibition video, which is a 40-minute spectacular video, beautifully produced, which runs through a worldwide scan of the origin of possible origin of zero in all cultures without prejudice. So thank you very much for watching, and till next week.